Having done a lot of preparatory work on determinants, we're now ready to prove some theorems. The first one is that a square matrix is invertible if and only if its determinant is non-zero. To do the proof, remember that we showed in video 26b that if you have a row operation R, then the determinant of the matrix A is 0 if and only if the determinant of R of A is 0. Using that lots of times, it follows that if you have a matrix A and you do a sequence of row operations and end up with some other matrix, then the determinant of the matrix you end up with is 0 if and only if the determinant of A was 0. That's all we need to make this theorem work. If A is invertible, there's a sequence of row operations taking A to the identity, so since the determinant of the identity is not 0, it must be that the determinant of A was not 0. And conversely, if A is not invertible, we can still do a sequence of row operations to take A to a row-reduced echelon form matrix, and that row-reduced echelon form matrix can't be the identity. If you've got a square row-reduced echelon form matrix, which is not the identity, it's got a column with no leading entry. We proved that in the lemma in video 24. It's got the same number of rows as columns, so it must have a row with no leading entry. But a row with no leading entry is all zeros. That means the determinant of this row-reduced echelon form matrix is 0, and since we reached the row-reduced echelon form matrix by doing row operations to A, the determinant of A must be 0 as well. The next theorem is the multiplicative property of the determinant. That says that if you have two matrices A and B, then the determinant of A times B is equal to the determinant of A times the determinant of B. You can find a full proof in the online notes. I'm just going to do the case where both matrices are invertible. Remember that we have showed before any invertible matrix is equal to a product of elementary matrices. As I say, we've done this before, but I'm just going to remind you why that's true. If you've got an invertible matrix, say X, then there is a sequence of row operations, let's say RK, R1 up to RK, which when you do them to that matrix X, gets you to the identity. But doing a row operation is the same as left multiplication by the corresponding elementary matrix. So if we let EI be the elementary matrix corresponding to the ith row operation Ri, then what we've got here is EK down to E1 times X is equal to the identity matrix. But we also know that elementary matrices are invertible. So multiplying on the left by the inverse of EK and then EK minus 1 and so on, we'll get that X is actually equal to the product of the inverses of the EIs. But in fact, this is an expression for X as a product of elementary matrices. The reason for that is that when we showed an elementary matrix was invertible, we did it in the following way. We showed that if E was equal to R of I, then we proved E was invertible by proving that its inverse was actually equal to the inverse row op applied to I. In particular, that inverse is obviously an elementary matrix, and therefore what I wrote here genuinely was a product of elementary matrices equal to our arbitrary invertible matrix X. But we already know the multiplicative property for left multiplication by an elementary matrix. That was the final corollary from video 26. It told us that the determinant of an elementary matrix R of I times an arbitrary matrix, which I'll call X here, was equal to the determinant of the elementary matrix multiplied by the determinant of the other matrix X. So in the case that we're going to prove, being invertible, we can write A as a product of elementary matrices, like this. Then when we use the corollary, K times, we get that the determinant of A is equal to the product of the determinants of the elementary matrices whose product was A. We can then do the same thing for B. If we write B as a product of elementary matrices like this, then the determinant of B, by using the corollary from the end of video 26 several times, L times, in fact, we'll get that the determinant of B is equal to the product of the determinants of the elementary matrices used in that product for B. But then it's now clear that, well, I mean, it's not clear, it's just obvious that A times B is equal to the product of the elementary matrices for A and the elementary matrices for B, and doing the same thing one final time gets us that the determinant of A, B is equal to the product of the determinants of the elementary matrices used in A and the elementary matrices used in B, but of course that's equal to the determinant of A times the determinant of B. We're done. Some easy consequences are, first of all, that the determinant of the inverse of a matrix is the inverse of the determinant of that matrix. The reason for that is that 1 is equal to the determinant of the identity, and that's equal to the determinant of A times its inverse, which is equal to the determinant of A times the determinant of A inverse by the theorem we've just seen. Finally, we're going to introduce row and column expansions for an arbitrary determinant. To define a row and column expansion, I need to introduce the ij minor of a matrix. We write the ij minor as A subscript ij, and that is the determinant of the matrix obtained by deleting row I and column j from A. Let's draw an example. Here is a matrix called A, then A 2, 2 will be the determinant of the matrix I get by crossing out row 2 and column 2 from A. That matrix is 1, 3, 7, 9. And you will notice that it's a determinant of a matrix which is 1 smaller than A. We can now define the ith row expansion and jth column expansion of the determinant of a matrix A. The ith row expansion is defined as the sum from j equals 1 to n of minus 1 to the power I plus j of the ij entry of A times the ij minor of A. You can see why this is called the ith row expansion. The entries of A, which appear here in the sum, are the sum from j equals 1 to n. Let me say this again. The entries of A which appear are the ones where I is fixed and j varies from 1 to n. That is, the entries in row I, so that's why it's called the ith row expansion. Similarly, the jth column expansion is the sum from I equals 1 to n of minus 1 to the power I plus j times the ij entry of A times the ij minor of A. And again, the entries of A which appear here are precisely the ones in the jth column, hence the name. Now, the fact which we won't prove here, if you'd like to see a proof, at least in a special case which will be enough to give an idea of how the general case would work, you should look in the online notes. But the fact which we won't prove is that row expansions and column expansions are equal to the determinant of A. So let's see an example of computing a matrix using a row and column expansion. I'm going to do it with this matrix here. In general, this is a stupid idea. You should use row and column expansions when you're computing determinants with matrices which have zeros in them. If you have a matrix with a lot of zeros, say in a particular row or a particular column, it makes sense to use a row or column expansion, because then a lot of terms in the row or column expansion will be multiplied by 0, so you wouldn't need to bother computing the smaller determinant. Here we're just going to do it as an example. So we're going to work out the first column expansion. This is the first column expansion of the determinant. So let's work out the terms one by one. First term when I equals 1 is minus 1 to the power 1 plus 1 times the 1, 1 entry of A, which is 1, times the determinant of the 2 by 2 matrix obtained by deleting row 1 and column 1. So here's row 1 and column 1. When we cross those out, the matrix we're left with is 5, 6, 8, 9. Next term in the first column expansion is when I equals 2. So I get minus 1 to the power 2 times 1 times the 2, 1 entry of A. The 2, 1 entry is 4. And then I multiply by the determinant of the 2 by 2 matrix obtained by deleting row 2 and column 1. When I delete row 2 and column 1, I'm left with the matrix 2, 3, 8, 9. The final term in the first column expansion will be minus 1 to the power 3 plus 1 times the 3, 1 entry, which is 7, times the determinant of the matrix obtained by crossing out row 3 and column 1. That's 2, 3, 5, 6. Finally, we've got a bunch of 2 by 2 determinants here which we can work out using our formula for a 2 by 2 determinant, and you'll see that what you get is minus 3 times 1 plus 4 times 6 minus 7 times 3, which is 0. Actually, we already know that the determinant of this matrix should be 0 because we've seen it before as an example. We computed its row-reduced echelon form. We found that row-reduced echelon form was not the identity. Therefore, this matrix is not invertible. Therefore, it should have determinant 0, and as you can see, it really does.